This lesson is going to examine how the exponent on a factor affects the behavior of the zero at that point. So we're going to look at three graphs to start with here. And the first graph is something from grade 10. This is a linear graph. Now the factor is x minus 2, which basically is like x minus 2 to the first power. In here, this is from grade 11. This is a quadratic. We have x minus 2 all squared. And over here, this is our grade 12 material. This is x minus 2 cubed. Now, all of these, and if you remember how we talked about factors and how it's related to the zeros or the x-intercepts, all of these have a 0 at 2. But now the exponents on these change it and how it behaves at that point. Now, this first graph is a linear graph, and we should know that the slope of this graph is 1, if you remember mx plus b, and the y-intercept is -2. And you can look at this on your graphing calculator as well to see that we would actually have a graph that's looking like this. So when we're looking at this, I had a factor of x minus 2 to the first power, and at this x-intercept, it's just going straight through the x-intercept. And that's with a power of 1, or an exponent of 1. The grade 11 in the quadratic, we still have an x-intercept at 2, but now this graph is opening up. It would have a leading coefficient that's positive, and it would be looking, if you examined it in your graphing calculator, or remember transformations and how this parabola would have translated 2 units to the right, we would have had a situation like this, where at that x-intercept, the graph is just bouncing off the 0 at that point. Now in grade 12, we now have a cubic graph, which again, if you examine this, it would have a leading coefficient. So that would mean its end behavior would be going down, and then on the right-hand side, it would be going up. So if we were looking at this, and if you examine again, if you examine it in your graph calculator, you're going to see this graph actually is doing something like this. So the behavior there, it's still going just through the x-intercept at 2, but now it's actually starting to just sort of, if we looked at it now, a little different, just starting to ride along there, and then it goes through it. So it makes a kind of special curve there. Now, these are all called or related to something called a multiplicity. So if we examine what that means down here, we're going to see that define multiplicity, this is a simple definition, but multiplicity is the number of zeros a function has depending on the exponent of that factor. So when we talk about it, it's going to be something like this. If the exponent is 1, like it was in this grade 10 example, it just has one single 0 at that point. It just goes right through. If the exponent is even, so a 2, a 4, a 6, an 8, anything that's even, it does one of these bouncing off things as it does in this grade 11 sort of example. It could bounce off going up. If we have a different function, it may bounce off going down, but no matter what, it's bouncing off that x-intercept. Now, if it's squared, as it is in the example that we have here, just to the power of 2, there's 2 zeros there. There's 2 non-unique zeros at the x-intercept of 2. If this graph was x minus 2 to the 4th power, it's still going to bounce off there, and you can examine in your calculator exactly how that's going to look, and you'd see that it would actually be just a little steeper, but it would still bounce off there. But this would actually, because it's x minus 2 to the 4th, you basically have x minus 2, x minus 2, x minus 2, x minus 2. We would consider that 4 non-unique x-intercepts or non-unique zeros at that point. This last graph, and we're saying here in the multiplicity, if the exponent on the factor is odd, it does one of these ride-along things. So here, there's actually an x-intercept at 2, but there's 3 non-unique x-intercepts there, because this function is actually x minus 2 times x minus 2 times x minus 2. So we would consider that being 3 non-unique x-intercepts. But they're all crossing at 2. Just their behavior there is a little different. So we're going to take this knowledge and we're going to look at some graphs. So we have these graphs down here that are actually talking about different degree graphs, and we're going to have to really look at how our windows are affecting it and what we know about different types of functions. So the first one, it says we have a degree 6 function. And if you look at the graph itself, it's doing something like this, which basically its end behavior is both up. So we know we have a leading coefficient, and here it's saying assume your leading coefficients were either positive or -1. So this is opening up, so we do have a positive leading coefficient. But we have to now relate our factors to make an equation to this graph. So right here, this is at -4. Here is -1. Here's 1. And here is 3. Those turn into factors that would be x plus 4. This one would be x plus 1. This guy is x minus 1. And the last one would be x minus 3. We talked about those in a previous class, how the roots and the factors are related. Our leading coefficient would be positive, so we could say there's a +1 out front, or we could just ignore it because it's +1 is just the same thing as not writing anything. But now we're saying we have to have a degree of 6 on this. And if I looked, I only have 1, 2, 3, 4 x's. So right now, I'm only at a 4th degree polynomial. So I have to look at their behavior at each spot and determine if it's just going through, if it's bouncing off, what the graph is actually doing at each x-intercept. So if I examine this first one here, and I could just trace it out, it's just bouncing off there. So I could say, if it's bouncing off, I could put a 2 there, make an even function. So now if I look, I still have those 4 original x's, but this one here is actually counting as 2 x's because I have the x squared. And I can go here. That's just going straight through, so that would be an exponent of 1. This guy's also just going straight through, so that's an exponent of 1. But if we look at this function here, it's actually doing, or this 0 here, it's bouncing off again, so that would be an exponent of 2 also. So the equation to this graph possibly could be, or is, x plus 4 squared, because it's bouncing off of x minus, or at x minus 4, going straight through at -1, so x plus 1, x minus 1 squared, and x minus 3. And that basically, if you look, I got 2 x's here, so 2, 3, 4, 5, and 6. I've matched the criteria for a degree 6 polynomial. So let's just move to example C right below it, because it is quite similar. We have a degree 4 function, and we should examine its end behavior. It's up, and it's up, so we know my leading coefficient is positive. And then I look at my x-intercepts. I've got here at -3, and I got here at 2. So those would turn into factors of x plus 3 and x minus 2. And I could have y equals, or f of x equals, with a leading coefficient that's +1, so we'll just leave it out. But now if I examine the multiplicity at those, because right now I only have 1x, 2 x's, that's x squared, so that would only be a degree 2 polynomial, but I need a degree 4. So when I look right here, this at -3 is bouncing off. This one's probably squared. Down here, bouncing off, it's squared. So now if you look, I've got 2 x's there, so 1, 2, and 2 x's here as well. That's 3, 4. That gets me a degree 4 polynomial, and that would be the equation of that graph. And you could check it in your calculator to make sure it looks similar. Now let's go up to question B. Now question B, if you look at your scales, you can definitely see that it's going up here past 50, past -50, but on my x-axis, it's just a little bit past 6 and a little bit past -5. So my window isn't showing the entire graph. And if you examine the degree of this, we have a degree 7. So that means this thing is having end behavior that's doing something like this. Now, that's not what the graph looks like, but if it's a degree 7, one arm goes up or one arm goes down. It's one of these situations. So we got to look at the graph and examine from left to right, what is this graph doing? Is it starting down and then ending up, or is it starting up and ending down? Now remember, when you graph these on your calculator, it's going to come up, and leaving stuff out, this graph is going to look something like this, which is saying it's going up to the right and down to the left, this is going to have a negative leading coefficient. So from up here, we would be able to assume that a is -1. So we could put that in there right away. And now we got to determine our factors. So right here, this was going through at -5. That relates to a factor of x plus 5. Over here, this is at 3. So that relates to a factor that's x minus 3. This x-intercept, or 0, is at 5. So that relates to x minus 5. And again, I'm going to look at this, and I can determine I only have 3 x's in here. I need to get to a degree 7, so I'm nowhere near where I need to be. I got to examine the multiplicity at those zeros and change the factors accordingly. So when we look now at this first factor at -5, it's just going straight through here. So this one will stay as a power of 1, or a multiplicity of 1. Now we don't need to write that exponent of 1. We can just leave it out. Now when we examine these through 3, it does this kind of ride along. So that means its power, or its exponent on that factor, has to be an odd number. So let's try a 3. That's odd. And here it's doing the ride along again at 5. So that again would probably relate to a power of, or an exponent of 5 on that factor. Now if we examine the number of x's we have, here I have 1, 2, 3, 4, 5, 6, 7. There's my degree 7 with a leading coefficient. Oh, we made a mistake here. Because this graph is actually doing this and going up, this is my bad. This should be a leading coefficient of +1. If it starts down and goes up, that's a leading coefficient of +1. So my apologies on that mistake. So there is my degree 7 with it going up. Now the last one, this is the one that if we were looking at it, it's saying a degree 5, and if we look, it's coming down and it's going up here. This now is a negative leading coefficient, so I would have a -1. Relating the x-intercepts to the roots, this is a x-intercept of -5, so that would turn into a factor of x plus 5. This is an x-intercept at 1, so that would turn into x minus 1. This is an x-intercept of 4, so that would turn into x minus 4. Now when we examine it, at this guy here, it's ripping straight through, so that would be a power of 1. At 4, it's going straight through, that would also be a power of 1. Knowing that I don't need to include those, I can get rid of the 1s on there. Now, we're looking for a degree 5. Right now we have 1, 2, 3 x's. I'm missing 2 more x's, but look what's happening at the x-intercept of 1. It's doing one of these ride-alongs. So that means I need an odd exponent. So here's an odd exponent of 3. So now if we look, I've got the 1 here. I've got 2, 3, 4 on this x, and 5. There's my degree 5 with the negative leading coefficient. There's the exponent of that graph. So when we're talking multiplicity, we're talking about the factors that are associated with the x-intercepts, and then looking at the behavior of the graph or the curve at that x-intercept. If it's going straight through it, it's a power of 1. If it's doing a bounce off, it's an even power of some sort, so 2, 4, 6, 8. And if it's doing a ride along there, it's some kind of odd power.